All right, hello. This video will be a pretty quick one, just going over the concept of Q, which is the reaction quotient, and kind of what it means with relation to K, the equilibrium constant. So they're the same expression in terms of products over reactants. The main thing to remember would be that the K is the ratio at equilibrium. So it's a very specific definition. The reaction needs to be at equilibrium, that you need to kind of hear that or see that phrase to know that you can plug it into K. So Q is just a quotient, which is just a ratio of products to reactants that might not necessarily be at equilibrium. Usually you want to use your initial conditions or initial amounts, and then you can tell if it's at equilibrium. So what you generally do with Q is predict whether it's at equilibrium or not, and if not, which direction it will shift. So this can basically predict a shift in the reaction, which will be more important when we get to ice tables. So what we would say is that you can have three scenarios. One would be, if K is equal to Q, then reaction is at equilibrium. This is going to be a no shift. Things at equilibrium will stay at equilibrium. So then we have K greater than Q, or possibly K being less than Q. I think it's good to learn to write K first. What's going to happen then is that the inequality arrow is going to point in the correct direction. So what this is going to mean is that the reaction is going to shift. So this is not equilibrium, so this is reaction shifts to the right to reach equilibrium. So make this red. And then in the case where K is less than Q, Q is greater than K, another way of saying it, is reaction shifts this way, because again, this arrow is going to match up with the inequality. So that's pretty much it. Write K first, and then use the same rules as before. You don't include solids and liquids. You want to have pressures in atmospheres or concentrations in molarity. Here's just a quick one from the worksheet where we have a reaction. We're given K, P, 0.25. So hold on to that. And then we want to state whether the reaction is at equilibrium. If not, which direction it will shift. So this is a classic question for just finding Q. Whenever you see this exact question, basically find Q. And we look at the reaction. We have the pressure of NO2. That's going to be squared because, again, of the coefficient of 2 in front of that. And then we have the pressure of N2O4. So we can just, these are in atmosphere, so we can just plug them in. This is going to be 0.5 squared over 1, which is 0.25. Comparing that to K, they are equal. So reaction is at equilibrium. Pretty easy. And for part B, we again just plug in the pressure of NO2, that's going to be in atmospheres, and we want to square that, and then we plug in the pressure of N2O4 in atmospheres, and then we get this to be about 17. So writing K first, we know K is 0.25, this is 17, that's greater than K. Arrow points left, so not at equilibrium. Reaction will shift left to reach equilibrium, or towards the reactant side. And again, when we do ice tables, we'll see that that would correspond to a change that would use up some of the products and create reactants. So kind of keep that in mind with this, again, is that this will predict the change row, or can predict the change row in an ice table problem. All right, well, that's pretty much it. Talk to you next time.